Okay guys, so this is your review video for your Unit 3 exam. First thing I want to go over a little worksheet that I attached to this study guide, which is how to find limits. It's kind of meant to be like a summary of everything we've learned. So we've been learning how to find limits of a function at some specific value, right? So the first thing you want to do is you always want to try direct substitution first, okay? Now usually that's not going to work. But there will be one or two questions on your exam where, just plugging it in, you get an answer. But that doesn't usually work. You usually have to do something to remove the discontinuity. And so when that doesn't happen, we have to try a bunch of different strategies to try to get that to happen. First of all, we have this. If you have a polynomial over a polynomial, you're going to either factor it or you can do L'Hopital. So for instance, if you guys saw something like this, well, then you're probably going to either factor it or you could do L'Hopital. Either one would work fine. Okay. The other thing is, what if you see a square root? If you have square roots involved, you're probably going to rationalize it. So we saw problems like this, right? We have x minus 1 over, I don't know. Just a quick example, I don't know. I don't know if that one would actually work, but the point is if you see a square root, chances are you're going to rationalize. Okay. We also talked about complex fractions. So whenever you see fractions inside of fractions like 1 over x plus 1 over x plus 1, probably going to have to simplify that in order to remove the discontinuity. I'm finding we just kind of have to treat ln as its own little thing, and also e to the x as its own little thing. In both cases, you're pretty much just going to use L'Hopital's rule for those two types of functions. Something that is kind of worth pointing out is that when you take the limit of a natural log function, I'm not sure why that didn't print all the way, as x approaches 0 from the right, it's negative infinity. We talked about why that is because they look like this. So as you approach 0 from the right, it goes to negative infinity. That's kind of the only detail you need to worry about here when you're trying to find a limit at x equals c. Now, after that, we only have one recourse at our disposal. If none of those things work, then the only thing left for us to do is to use a table. Okay, so if you can't remove the discontinuity with one of these strategies up here of simplifying, rationalizing, or using L'Hopital, the only thing you can do is use a table. So, if you have something where it doesn't work, just make a table, plug the number in the middle, find something to the left and right, and see what you get. And that's pretty much your only recourse at that point. So that was how you find limits at some specific number, but what about when you're trying to find limits at infinity? Well, let's go ahead and take a look at that. We talked about a few strategies. First of all, what if you have a rational expression? Same thing. It's like a polynomial over a polynomial, but I wrote it a little bit differently this time. When you have a polynomial on the top, polynomial on the bottom, basically you can compare the powers there. And if the power on the top is less than the power on the bottom, then the limit at infinity will be 0. If they're equal, then the limit will be the ratio of the coefficients. And if the one on the top is bigger than the one on the bottom, your limit's either going to be positive infinity or negative infinity. And you'll find out what that is by just plugging in the infinity and seeing what you get using some basic properties of infinity. Also, we talked about how to find limits at infinity when you're dealing with trigonometric functions. So the first thing to keep in mind when you're dealing with trigonometric functions is the fact that, the limit of a trigonometric function at infinity does not exist. They always oscillate. They always go up and down. But based on that, we have a few other things that we looked at. First of all, if you have an oscillating function at infinity and you multiply it by a function that goes to 0 at infinity, then ultimately the 0 wins and the limit will be 0. Or if you have an oscillating function, you multiply it by infinity, that infinity causes it to oscillate even more, so that one doesn't exist. Or if you have an oscillating function being divided by a function that goes to infinity at infinity, then the infinity kind of overwhelms the oscillation and just goes to 0. But that only applies to sine and cosine. Now, if you I don't plan on giving you any questions like this, but I just thought it was worth talking about. If you have a tangent or cotangent, cosecant, or secant function in the numerator, they oscillate as well. But the problem is they don't oscillate between two numbers. Like sine and cosine oscillate between 1 and -1. So the infinity causes it to go to 0 in the long run. But tangent, cotangent, cosecant, they all have asymptotes, and they themselves go to infinity repeatedly. And so what you end up with then is an infinity over an infinity situation, and it also oscillates in two different directions. It's negative on the left, positive on the right. So we're just going to say for those ones it doesn't exist. But like I said, I don't plan on giving you anything like that. Just wanted to mention it. So for this, you can kind of just like put an X through it. I'm not going to test you on any of those things, but I just wanted to mention it. You will see something like this, though, with the sine and the cosines. Finally, if you have infinity over an oscillating function, that's also does not exist. Okay, so there's your how to deal with trigonometric functions at infinity. We also learned how to deal with logarithmic functions and exponential functions at infinity. Logarithmic functions, they go to infinity at infinity, and so do exponential functions. Exponential functions are a little bit different, though. At negative infinity, they go to 0. But regardless, in both of those circumstances, what you're going to end up doing is you're going to end up using L'Hopital's rule. And so that's basically a summary of everything. So if you decide to use notes on this test to cap your grade at a B, bring this. I don't know if it's helpful to you or not. If you find that you use it during the study guide practice, feel free to bring it. You might appreciate having it with you. You can also bring all the flashcards that I printed for you or put up on Google Classroom for you. So anyway, there's our thing. So let's go ahead and jump in and we'll get started on the study guide. Let's see, where is our study guide? Here it is. Let me zoom in a little bit and we'll get started. So I'm just going to work through every problem. Just fast forward to the question that you want help with. You don't have to do all of these. Let's go ahead and begin. So, number 1, a table of selected values for the function f of x is given below. Use the table below to complete the statement. So they want us to find the limit of this function as x approaches 0. So here's where x is approaching 0. And you do want to come from the left and the right when you're taking a limit, unless it has a little plus or a minus, in which case you have a one-sided limit. So in this case, we're coming from the left and the right. The limit is going to be the y value. So what y value are we approaching? The function is undefined at that point, but we're still approaching a y value. Here, to the immediate left, it looks like it's really close to 0.5. And the same thing on the right. So it seems like it's trying to approach a value of 0.5, and we would say that the limit, therefore, is 0.5. Okay? Let's go ahead and move on to number 2. A table of selected values for the function g of x is given below. We want to find what is the limit of g of x as x approaches 0. So once again, we're approaching 0 from the left and from the right. Now from the left and right, they're different. You're noticing, first of all, that this one's negative 1,000, this one's positive 1,000. So right away, we know that the limit doesn't exist. But when the limit doesn't exist, sometimes you can write infinity, sometimes you can write negative infinity, or sometimes it's just a jump discontinuity. And here's what I want you guys to understand here. Look at these numbers. I don't want you guys to think the limit from the left is negative 1,000, because it's not. What's happening here is look how much the x is changing, by 1,000th. So the difference between here and here is only by a very minuscule amount, but look how much the y value changed. That tells me that the y value is decreasing extremely fast, which means that if I go one more step closer to 0, it's going to be even smaller than this. It's going to be like negative 10,000 or something. So I don't want you guys to think it's reaching a limit of 1,000. It's not. What's happening is the y value is dropping very fast as we approach 0. Now on the right side, it's increasing very fast. So the limit from the right is positive infinity, and the limit from the left is negative infinity. And because the limit from the right and left are not the same kind of infinity, we're just going to say does not exist. Okay? And yes, you do have to put does not exist. Or if you can put infinity, then you should put infinity or negative infinity. You have to be very specific with your answers. All right, let's go ahead and move on to number 3. A table of selected values for the function h of x is given below. So here we go. This one's asking for a specific limit. This is asking for the limit from the left as I approach 0. So I'm approaching 0 from the left. What y value am I approaching? Let's take a look. 1.41, 1.498, 1.499. It looks like it's approaching 1.5 from the left. How about from the right? As I approach x equals 0 from the right, what's the y value approaching? Well, it's 1.81. Kind of covered up my numbers so I can't really see it now. Negative 1.81, negative 1.92, negative 1.99. Looks like it's approaching really close to negative 2, right? So this one was 1.5, but this one's approaching negative 2 from the right. So the limits from the right and left are not the same, so therefore we would say the limit of this function at 0 does not exist. H of 0 does exist, though. That's just what is the y value when x is 0, and the y value is 1.5. So what we have then is we have a graph, right? We're approaching x equals 0, and as I approach x equals 0 from the left, we're approaching like 1.5. But as we approach from the left, we're approaching negative 2. And so solid dot up here because it actually equals 1.5 at 0. Open dot down here because it doesn't equal negative 2 at 0. All right. Those pictures I drew will probably help us answer a few of the next questions that are coming up. And so the question is, can you draw those pictures as you look at these tables? In questions 1 through 3 above, you were given tables of 3 functions. Which of those functions were discontinuous? Pretty sure the answer was all of them. Okay? Now, but they were discontinuous for different reasons. Okay? So let's go back to number 1. On number 1, you may recall that the limit actually existed, right? But the function's not defined. So let's talk about this. In order for a function to be continuous, the function has to exist at that value, the limit has to exist at that value, and they have to be the same thing. Now, for number 1, the problem is that the function didn't exist. F of c was undefined. In number 2, that was the one where it went to infinity on the left and right. Now, honestly, you could say that f of c is undefined again because there was no answer where the c value was, but the limit was also non-existent. So you could have said 2 different answers. Just one of them is needed to have a correct answer, though. And for number 3, the function did exist. In case you don't recall on that one, I'll zoom back really quick. Let's go back to number 3. On number 3, you might recall that the limit from the function equaled 1.5. But the problem is the limit from the left was 1.5, the limit from the right was negative 2. So that means that the limit did not exist, right? So even though the function existed, the limit did not. So on this other problem that we're talking about now, we only have one reason to say that the function didn't exist. I'm sorry, not exist, that the function was discontinuous, and that was because, let me make this pretty here, the limit did not exist. The limit as x approached our number, which was 0. I guess on all of these I should have had 0 in here because it wasn't, we knew what 0 was, what the c was. The c we were approaching was 0, so we should probably use the number we're approaching. So the limit as x approached 0 for the function did not exist. I'm also using the wrong letters here. I think for number 1, I think that was f of x, and I think on number 2 it was g of x, and then on number 3 it was h of x. So I need to be a little more specific in my writing. So number 1, the function was f of x was undefined at 0. Number 2, it was discontinuous because the function was undefined and because the limit did not exist. And for number 3, the function h of x was, the limit did not exist. Therefore, none of those functions were continuous. Okay. Now for number 5, questions 1 through 3 above, you were given tables of 3 functions. Which of these were likely to vertical asymptote? You may recall that was the one where I drew this thing that went like this, right? So that was number 2. In questions 1 through 3, you're given a table of 3 functions. Which of these had a removable discontinuity? So a discontinuity is removable if the function doesn't exist, but the limit does. Okay, so on number 1, that is the one that had a removable discontinuity. Here's why. Because on number 1, remember, the function didn't exist at 0, but it did have a limit of, what was it? I forget now. I have to cheat and look back. I forgot. It was 0.5. Trying to get this thing to sit right. Okay, so the limit did exist. It was 0.5. And so what that function would look like, it would look like at 0, right? It approaches 0.5 from the left and from the right, but the function just doesn't exist there. So there's a hole. But as you can see, the limit exists. And that's what we call a removable discontinuity. So number 1 is a removable discontinuity. Number 7, in questions 1 through 3 above, you're given tables of functions f, g, and h. Which of these functions had a jump discontinuity? That would have been number 3. You could tell because those are the ones that look like this, right? But how can you tell from the table? It's when the limit as x approaches 0 from the left is not equal to the limit as x approaches 0 from the right. Now, technically, you could say this is also true for number 2, but on number 2, you remember they weren't the left and right-handed limits didn't exist either. They were both infinity, so we can't say that's a jump discontinuity. That's a vertical asymptote. But when the left-hand limit exists and the right-hand limit exists, but they're not the same thing, that's when you have a jump discontinuity. Okay? So those are some questions that you might expect to see about tables on your next test coming up on Thursday. Let's take a look at some other questions here involving graphs. So we looked at questions about tables. Now we're going to look at some tables about graphs. So let's read our instructions here. It says we have j of x, we have k of x, and we're going to find the limits. If it's a non-existent limit or it's an infinite limit, then we have to say if it's infinity or negative infinity. If it's neither of those, then you can write does not exist. And it tells us where our vertical asymptotes are. So it tells us that j of x has a vertical asymptote here at 0. It also tells us that we have a horizontal asymptote at y equals 3 on this function. So there's a flat imaginary line here. All right, so I got to zoom out a little bit here to answer these questions. Sorry about the size of all this. Try to make this fit a little bit better. Okay, so let's begin. So number 1, what is the limit of my function? It looks like it's probably a j of x as x approaches 1. Okay, what is the limit of j of x as x approaches 1? So when it says approaching 1, that means we're approaching from both directions. Now this is where x equals 1 right here, and from both directions it's approaching a positive 3 from both directions. So the limit exists, and we would say that it's 3. Now what is the limit of j of x as x approaches 0 from the right? So I'm approaching 0. Here's where x equals 0, but I'm approaching it from the right, and that reaches that point right there, which is about 2. Now if we try to approach 0 from the left, we jump down to negative infinity. Next question, what is the limit of j of x as x approaches negative infinity? This means as I go to the left forever, what y value am I reaching? So as I go to the left forever, it's bottoming out at this horizontal asymptote of y equals 3. I'm going to clear these off so I can have some more writing space. All right, next one. what is the limit of j of x at positive infinity? So that means as I move to the right. And as I move to the right forever, it looks like it never stops going up. So we're going to say positive infinity there. What is the limit of j of x at -2? At -2, from the left and from the right, it's approaching this open dot, which looks to me like it would probably be about 2.5 for the y value. Number 14, we're using our properties of limits, and pretty much how limits work with properties is whether you're multiplying, dividing, subtracting, adding, squaring, or whatever, what you do is just find the limit of each one separately and then do whatever operation it's indicating. So in this case, I'm going to find the limit of j of x at 2, I'm going to find the limit of k of x at 2, and then I'm going to multiply those two answers at the end. So the limit of j of x at 2 is 4, and the limit of k of x at 2 is 6. I'm going to multiply those and I get 24. So there's our final answer for number 14. Now j of 4. Now we're on the j function. You got to be careful in this test to make sure that you're looking at the right one. So we're on j here, right? So I want to be on this function over here. J of 4 is where the closed dot is. So here's where x equals 4 and the closed dot is here. So j of 4 is actually going to be 2. K of 0, now I'm on the k function. K of 0 does not exist. There is no closed dot anywhere. So we're going to say does not exist. Now as for these guys, you got to remember how to do it. What you do basically is you start by moving the limit to the inside function. So it's going to be k of the limit as x approaches negative infinity of j of x. So we're going to find the limit of j of x at negative infinity. Now we did that earlier. The limit of j of x at negative infinity is 3. So that means we really just want to find what is k of 3. K of 3 is 4. So the final answer there would be 4. This one, oh, did I put it in the wrong spot? Oh, you know what I just did? I found the limit of k of x at negative infinity, right? So that was this one that I did, so that's 4. Let me jump back and do this one. So for this one, I want to move the limit to the inside. We're approaching 1, and it's k of x. So what is the limit of k of x at 1? At 1, the limit of k of x is 3. So now we need to know what j of 3 is, and j of 3 is 5. Okay, same thing here. This is a one-sided limit. Back to this one though. When we did this, the limit of k of x at 1 was here. And notice that's the same from the left and the right. So whether you're coming from above or below, right, it's approaching the same y value of 3. So that means that when we're looking at j of 3, right, whether we're coming from the left or right, it's approaching the same one. So remember, with these composite functions, you got to be careful. If it's coming at it from both directions, remember, on the inside function, below and above corresponds to left and right on the other graph. On this function, it doesn't really matter because both above and below, which is left and right over here, meet at the same point, so it doesn't matter. But you got to be careful with that. Let's go ahead and move on to the next one. On this one, we're looking at -2 from the right. So I'm going to be approaching -2 from the right of my k of x function. Okay, so here we go. Here's -2, and I'm approaching it from the right. That would be here. So I'm approaching -2 and I land there. So I land at 0. That is true. But even though I'm landing at 0, I'm coming at that y value of 0 from underneath of it. which means that I'm coming at that y value of 0 from numbers that are less than 0. Now, when I transpose over here to the j function, if I'm coming at 0, but now this is an x value, right? If I'm coming at 0 from smaller numbers than 0, that means I'm approaching 0 from the left, and that's going to give me negative infinity. So the final answer on that one would be negative infinity. Let's go ahead and take a look at the next one. Once again, we're going to move the limit to the inside function. So we're approaching -2 from the left of the k function. Now, if I'm approaching -2 from the left, now I'm coming at the same y value of 0, but this time I'm coming at it from numbers that are above the 0, or in other words, greater than 0, which over here means that I'm approaching an x value of 0 from numbers greater than 0, which means I'm approaching 0 from the right, and in this case, I end up with a limit of 2. So, remember that one. When you're doing these composite functions, one-sided limits have to be treated, and double-sided limits too, honestly. You've got to think about left and right. On your first graph, above and below corresponds to left and right on the other one because it goes from a y value to an x value. All right, so there's the end of the graph questions. Actually, I think there's a few more down here. Let's take a look. Question number 21 says, where are the discontinuities, and explain why each one is a discontinuity? And we're only looking at the graph of j in this case. I'm going to need a little bit more writing space here. So let's look at j. Where are its discontinuities? Well, there's one here. That's at x equals -2. There's one here at that vertical asymptote point. So that's at x equals 0. And there was one up here as well, where there was an open dot, so that was x equals 4. Now, we have to explain why they are discontinuous. Now, remember, in order for a function to be continuous, the function has to exist at that point, the limit has to exist at that point, and those two things have to be the same. If one of those three things fail, if either the function fails to exist, the limit fails to exist, or they're not equal, then that's a reason for saying it's not continuous. So let's go ahead and take a look at x equals -2. So question number 1, does the function exist? The answer is no. So in this case, j of -2 does not exist. So there, or you could say is undefined. So it's discontinuous at -2 because there's an open dot there with no filled in dot, which means the function just doesn't exist there. Let's take a look at 0. Now we can't say that the function is not defined at 0 because there is a closed dot at 0. Does the limit exist? No. So in this case, we're going to say the limit as x approaches 0 for the j function does not exist, because the limit from the left is -infinity, but the limit from the right is 2. So the limit fails to exist for that one. What about at x equals 4? At x equals 4, the function exists. So we have j of 4, and that j of 4 happens to equal 2. So the function exists at that point, right? The limit also exists. From the left and from the right, we're approaching a y value of 6. So the limit as x approaches 4 for the j function also exists. It's 6. The problem is they're not equal to each other. So in this case, we would say that it's discontinuous at x equals 4 because even though the function exists and the limit exists, those two things are not the same. Okay? Now you need to know how to write these. This is important that you know how to write these correctly, but they're really easy to identify. You're going to say an answer like this anytime there's no closed dots. You're going to say an answer like this anytime the limit from the left and right are different. You're going to say an answer like this in a very rare circumstance. You're going to use this answer only when you have one of those situations where there's a hole with a dot below it or above it. That's the only time you're ever going to use that one. Okay, so there's that. It also asks us to ask which discontinuities are removable. So we've talked about that. remember, a discontinuity is removable when, even though the function doesn't exist, let me rewrite that. A discontinuity is removable when f of c is undefined, but the limit of your function as x approaches c actually exists. So we had three discontinuities. For which of these three discontinuities did the limit exist, but the function didn't exist? And that would be this one right here. Here, the function was never defined. It's not defined anywhere. But but the limit does exist. Now, I guess actually I need to revise what I'm saying. I believe this is technically also a removable discontinuity. So I'm going to go ahead and put both of those. We're going to say x equals -2, and we're going to say x equals 4. Now, why am I saying x equals 4? So maybe I should rephrase this a little bit to be more inclusive. So a discontinuity is removable if the limit exists, but f of c is not equal to that limit. That's probably a better way of saying it. Okay, so in this case, the limit exists, but the function doesn't equal it because the function doesn't exist. In this case, the limit exists, but it doesn't equal the value of the function at that point. So in both cases, you have a removable discontinuity. Now, the quick and easy way to identify it basically is just to understand that removable discontinuities, they always look the same. So this is the technical way to write it, but here's how you can tell the answer. Removable discontinuities look like holes. That's it. So that's a hole and that's a hole. Okay. Now this is not a hole, right? Because it's a jump discontinuity. But hopefully you guys have the idea there. So it's when the limit exists, but it doesn't equal the value of the function at that point. All right. So that takes care of the limit questions pertaining to graphs. Now we move on to just a hodgepodge of other things. The next few questions are, like I said, they're just kind of like a bunch of random things that we've learned. I couldn't really find a way to organize this in any meaningful way. It's just a bunch of stuff that we're going to look at. The next big group of things we're going to look at is numbers 28 through 50. On those questions, we're talking about finding limits of equations. But for 22 up to 27, it's just kind of like a mixture of different things that we've learned that I do want you to know how to do. Okay, so we'll call this the hodgepodge section. So we talked about tables, we've talked about graphs, now we have a hodgepodge section of just random things. So, and this is one question I'll ask you. It's a very popular AP question. It's where they give you a function, and your job is to find the value of k so that this function turns out to be continuous. Now, for a piecewise function to be continuous, the limit of your function from the left of your breakpoint has to be the same thing as the limit of your function as the right of the breakpoint. Now, another little subtle detail that's easy to miss is it also has to equal the value of your function at that point. Now, I'm not going to be making much use of this fact to solve this problem. The only time when you have to worry about this not being able to happen is if they don't have an equal sign on one of these, because at that point that means the function just can't equal that number. But in this case, it does, so we don't really need to worry about this. So all I need to do is I need to make sure that the limit of my function from the left of pi is equal to the limit of my function from the right of pi. So left of pi means less than pi. So that would be this one. So the limit of my function, which is now from the left, it's going to be sine of 2x as x approaches pi, is that as I'm approaching from the left. Now from the right, that from the right of pi means greater than pi, and greater than pi is here. So the limit as I approach pi from the right applies to this piece of my function. Now in this case, both of these, we're just going to do direct substitution. So plug them in for x, right? So sine of 2 pi is 0. And plugging in pi here, you get 2 pi plus k. Now remember, we're trying to find the value of k, so I want to get k by itself. So I'm going to minus 2 pi on both sides, and I end up with negative 2 pi. And there you go. So the answer would be A. So you'll definitely see one of those on your exam. Let's go ahead and continue into the next sets of questions. All right, for numbers 23 and 24, explain why the function is not continuous. So remember, we've talked about this many times. This is a big question, obviously, right? So you want to make sure you really know how to do this. We've seen this like a bunch of times today. So how do you know if a function is not continuous? Either f of c doesn't exist, the limit doesn't exist, or they're not equal. So it's got to be one of those three things. Okay? So let's take a look at this function. They want to know, why is this function not continuous at c equals negative 1? Well, let's see. Let's make sure the function actually exists at that point. That's undefined. So right there we can stop. We could say that this function is not continuous because f of negative 1 does not exist. So here's our answer for number 23A. So for part A, we're going to say f of x is not continuous at x equals negative 1 because f of negative 1 is undefined. There you go. Good enough. All right. Let's go ahead and take a look at the next one here. Part B. Let's see here. Actually, let me back up here to part A a little bit. So for part A, I don't want to leave it there. Even though the answer is good, I know what's on your guys' test, and so I want to prepare you guys a little bit more for this question, because here's another question I can ask. I could ask you, what kind of discontinuity is it? Is it removable or not removable? Now, if it's removable, that means that the limit at negative 1 does exist. We've already proven the function's doesn't exist, but does the limit exist? Well, as you can see, we can use factoring here. And we can remove the discontinuity. And then we can do direct substitution to get negative 2. So I want you guys to understand that on number 1, it is not continuous because the function doesn't exist. But what I want you guys to understand is that since f of negative 1 is undefined, but the limit as x approaches negative 1 for that function does exist, it equals negative 2, this is a removable discontinuity. So I want you guys to be able to tell that too, because I think on the exam, I'm going to want you to do a little bit more than just telling me whether it, why it's not continuous. I might ask you, what kind of discontinuity is it? Is it removable or non-removable? So let's go ahead and take a look at part B. Now in part B, once again, f of 2 doesn't exist. If you tried plugging in 2, you get undefined. But the problem here is that the limit doesn't exist either. Because this is not a removable discontinuity. There's no factoring or anything you can do to get rid of that limit. And so this is a non-removable discontinuity. Okay, so that's kind of the big thing I want you guys to take away from here with 23A and B is, yes, can you tell me why it's discontinuous, but also can you tell me whether it's removable or not? I probably should have changed the instructions here. Tell me, is it a removable or non-removable discontinuity? Anyway, let's go back, and we're going to move on to number 24 now. On number 24, explain why the function is not continuous at the indicated value of c. Is it because, now in this case, the indicated value of c is 1, so we're looking at this spot, obviously. Is it because f of c is not defined? No, it is defined. Is it because the limit doesn't exist? No, because the limit does exist. Is it because the limit is not the same as the function? The answer is yes, so that's the reason why. Remember that this is the situation that's going to happen when you have a hole with a dot above it or below it. The next few questions are questions about the intermediate value theorem. You'll see maybe like 1 or 2 questions like this on your multiple choice, but I'm going to be hitting this one up a little bit more heavily on your free response question. So, if p of x is a continuous function on a closed interval 1 to 3, and p of 1 is less than or equal to k, which is less than or equal to p of 3. Right there, there's your classic IVT. If you see that, you guys should think IVT right away. If you did the extra credit on squeeze theorem, that it also kind of looks like that a little bit, but there's your classic IVT setup. And c is in that interval, then which of the following statements must be true? Okay, so which one of these is the correct way to finish the IVT statement? The answer is C. There is at least one value of C such that P of C equals K. You can't say there's only one. Okay, we know that none of these fit the criteria at all. Now the reason why I actually pulled this from a test prep material book, and the reason why this might be tempting is because there's actually other theorems we're going to learn this year that look a little bit like this, and so people might be tempted to pick one of these. But in this case, it's not as hard for you guys because there's only one thing it can be. It's either C or D, and hopefully you guys remember it's C. It's at least one. Okay. The point is that we have some function, and we're going from 1 to 3, and P of 1 is less than P of 3, and K is somewhere in the middle. Now, it's possible that it crosses that K line only once, but it could technically cross it a few times, right? And so we can't say that there's only one value of C such that P of C equals K. There's at least one. And so the answer is C. That's the IVT theorem. Let's go ahead and take a look at number 26. Number 26 is more run-of-the-mill stuff that we did in class. Use the intermediate value theorem to prove that there exists at least one value of C for which f of C equals -3 on the following interval and function here. So the steps I gave you in class was identify your A and B. Those are the beginning and ending points of your interval. Identify your K. Identify what K value you're trying to reach. Make sure that your function's continuous. That's a linear function, so it is continuous. And then we're supposed to find out what f of -1 is, and we're supposed to find out what f of 5 is. So we're going to plug in -1, and we're going to get 7. We're going to plug in 5, and we're going to get -10 plus 5 is -5. And we would just want to make sure that -3 is in fact in between there. -3 is greater than 5 and it's less than 7. So that's the other requirement, is that our K value has to be in between those things. Now you might notice, by the way, that if you're comparing this problem to our notes that we did in class, in our notes in class the arrows went the other way. But that's because for this function, when I plugged in a smaller x value than over here, it actually gave me a y value that's bigger than the y value over here. So I'm making the arrows go the other way. Hopefully you guys know which way is greater than and which way is less than, etc. You always think just Pac-Man. Pac-Man always wants to eat the bigger number, right? So in this case, Pac-Man's going to the left in terms of bigger numbers. Anyway, so there's all your criteria, and now we're just going to go ahead and say our statement. That's all you have to do. We check to make sure that everything's true, and now we say, since f of x is continuous on the interval -1 to 5 and goes from -5, that's the lowest y value. Or I guess you could start with the highest one, it doesn't really matter. And it goes from 7 to -5. There must be some value c such that f of c equals our k value of -3. So in other words, I've got a function here. You don't have to draw this, but the linear function, negative 2x plus 5, would look something like this, right? And we're going from -1, which is here, to +5, which is here. And they want to know, is there at least one place where k equals, what was it, 3? Or -3, sorry, right down here, not there. And the answer is yes, there is one. So since this is a continuous line and we're going from a y value of 7 to a y value of -5, at some point that line has to cross a y value of -3. Okay. All right, another way this IVT theorem can be applied with a question is with these tables here. Selected values of the continuous function f of x, notice it says continuous, that's one of the requirements for IVT, are provided in the table below. What is the least number of times that f of x equals 4? Well, f of x is jumping from 0 to 5, and it's a continuous line. So if it's going from 0 to 5, at some place along the way, it must have crossed 4. Same thing here. If you're going from 5 to 3, and it's a continuous line, at some place it must have crossed 4. And same thing here. If you're going from 3 to 9, at some place it must have crossed 4, and also again here. So it looks like there is 4 places where it had to equal 4. So the answer is there is at least 4 times that this function equaled 4 along the way. And mind you, it could have been more. It could have crossed 4 multiple times on its path from 0 to 5, but it had to do it at least once, we know. That's your IVT theorem here. Okay, now we're getting into the fourth major chunk. So we started by talking about tables, then we moved on to talking about graphs, then we had a hodgepodge of things. Now we're going to talk about this part. This is a big part of your test too, guys. You know, you need to be able to find limits of equations, and this is where that handout that I gave you guys is going to come in pretty handy, this thing here. So we have 2 major types of functions. Functions where you're finding a limit at a specific number, and functions where you are finding limits at infinity. So going back to our study guide here, for the first one, I'm finding the limit at a specific number. It's pi over 4. And when you're trying to find the limit at a specific number, the first thing that you always do is you start by doing direct substitution. Always try direct substitution first. So let's do that. So can we just plug this in? I know you guys don't like trig, but let's see if it works. Now, cotangent of pi over 4. I don't know if you guys remember your values, but cotangent is cosine over sine. Pi over 4 is that spot on your unit circle, which is right here, right in the middle. And when that happens, both the x and the y value are radical 2 over 2. So what we end up with here then is negative radical 2 over 2 over radical 2 over 2. Now we could make this hard by trying to simplify this, or we could just realize, oh, they're exactly the same, so they cancel and you're left with negative 1. So the limit exists. By direct substitution, the answer is negative 1. Okay. Now if this were an FRQ, you could risk it and try just to leave your answer like this and hope that direct substitution works. But if it turned out that this didn't exist, you would get it wrong. But on a multiple choice, you do need to know how to work it down to that point. So if you do plan on using notes, I don't know how mean I'm going to be with the trig functions on this, but you can always bring your trig tables and stuff. I don't encourage it. I would like you guys to know those because you can't use them on your AP exam. So I would really encourage you guys to make sure you're still working on memorizing those. But if you need them, you can use them. Capture grade. All right. Here we go. Once again, we're finding the limit at a number. We're not finding the limit at infinity. So we always start with direct substitution. So let's do that. I get negative 3 plus 1 over negative 3 squared minus 4 times negative 3 plus 4. That gives me negative 2 over 9 plus 12 plus 4. So there's not 0 in the bottom. So once again, direct substitution works. This is 21 plus 4 is 25. So the final answer there would be negative 2/25. Okay, so direct substitution works. Let's move on to the next one. On this one, direct substitution is not going to work. If you plug in 3 to the top, you're going to get 4. But on the bottom, you're going to get 9 minus 18 plus 9. The two positive 9s make a positive 18. Minus 18 makes 0. And so we have a sad situation here. And so the next thing that we do, once direct substitution fails, if that doesn't work, we're going to try one of these things. Do I have a polynomial over a polynomial? Do I have a square root or a complex fraction, a natural log, or an e? Well, in this case, we have a polynomial, right? It's polynomial over polynomial. And when that's the case, you can either factor or L'Hopital. You don't need to try both. If this one fails, L'Hopital is not going to work either. If L'Hopital doesn't work, then factoring is not going to work. But in this case, actually, you can't even do L'Hopital anyway because we got 4 over 0, right? And that is not a L'Hopital situation. L'Hopital has to be 0 over 0. So here we go. What we do then is we try to factor it. And by the way, since L'Hopital fails, factoring is not going to work either, but I'm going to pretend I don't know that. If I factor this bottom, I get x minus 3 times x minus 3. Does anything cancel? Nope. And so when that happens, when your only methods that you had available to you fail to remove the discontinuity, then you have a non-removable discontinuity. And in that case, you have to use a table to get your answer. Okay? So in this case, we're going to have to use a table. It's either going to be infinity, negative infinity, or undefined. So I'm going to put 3 there. We already know it's undefined there. So we're going to pick a number to the left of 3 and a number to the right of 3. And we're going to have to use a calculator. So now the big question is, will you be allowed to use calculators on your test? I guess I would have to if I'm going to give you questions like this, right? So let me expand this out a little bit. Okay, you can type it in however you want to. You can do it by hand, or you can use the strategy I shared with you guys a little while back, where you type the function in first. So parentheses x plus 1 is in the numerator. Got to put it in parentheses. Divided by parentheses again for the denominator. X squared minus 6x plus 9. Okay, then we go back to the home table here. And what we're going to do is we're going to go to variables. We're going to go to y variables, 1, y1. And we're going to plug in the numbers that we're working with here, which is 2.999. And when I plug that in, I get a really big positive number. So that means it's going to infinity on the right, on the left side. Let's repeat this process. If you forgot how to just bring this all back up again, you push second, enter, and it brings the whole thing back. And you just type in the numbers that you do want. And I get another really big positive number. So it's going to infinity on both sides. And therefore, we can say that the final answer to this particular problem is goes to infinity. Now, whether or not you're allowed to put equals infinity, I'm not sure. So it's probably safe just to say goes to. Let's go ahead and take a look at number 31. Once again, we try our direct substitution first. So let's try that. -2 tangent of 2 times 3 pi over 4. The 2 can reduce with the 4 to make 2. And tangent is sine over cosine. Now, as you guys might recall, 3 pi over 2 is down here. And down there, cosine is 0 and sine is -1. So as you can see, we have a discontinuity there. Now, it's not L'Hopital, right? Because it's not 0 over 0, so we can't do that. So the only thing we can do is a table. I didn't really give you guys any, when you're finding the limit at a number, notice I didn't really include anything about trig functions here. And that's because when you can't do the limit of a trig function, there is no limit. It's going to be positive infinity or negative infinity or does not exist. So I didn't even bother including a category here when you're trying to find a limit at a specific number for a trig function. So basically, if you have a discontinuity with a trig function at a number, then it's non-removable and you're going to have to use a table. Now, let's go ahead and see how we use a table here. For this one, making a table, my x value I'm approaching is 3 pi over 4. We already know it's undefined there. And now we need to pick a number that's slightly smaller than 3 pi over 4. How in the heck do you do that? Well, we got to think a little bit outside the box here, guys. What is 3 pi over 4? 3 times pi divided by 4 is 2.356, right? So 2.356. So if I take 1,000th off, that's 2.355. And if I add 1,000th, remember 1,000th is like this, I'm taking out 0.001. In other words, I take 1 off the last number. And if I add 1,000th to that, then I get 2.357. So we're going to go ahead and plug those into our calculator, figure out what's happening on the left hand and right hand of this particular function. So we'll go ahead and type it in. What was the function? It was -2, and it was tangent of 2x. We'll go back to our thing here. We're going to bring up the y variable again. We're going to plug in to the left 2.355. And I get a really big negative number, so we can assume it's going to negative infinity on the left. Let's see what's happening on the right. Second enter brings back the same expression, and this time I'm going to plug in 2.357, and I get a really big positive number. So on the left it's negative infinity, and on the right it's positive infinity, and therefore we can just say, since the left and right are not the same, we're going to say the limit does not exist. Okay? Let's go ahead and take a look at number 32. All right, so in this case, we're finding the limit of a number, right? So when we do that, we always try direct substitution first. That's going to give me 2 over 4 minus 4, which is 2 over 0, and so it fails. It's not a L'Hopital question, and it's polynomials. Now, you can't factor this and remove any discontinuities either. Even though we can factor the bottom, it won't cancel anything on the top out, so we're stuck with it, which means the only thing we can do is, once again, a table. Now, here's what's cool about this one. We only have to find the limit from the left. I'm sorry, from the right. It's a positive 2. So we're approaching -2. It's undefined, but we only need to find a number to the right of it. So what's happening to the right? So at what's 1,000th bigger than this? That would be 1 point. It's not positive, though. Let me back up a little bit. -1.999 is what you would get if you added 1,000th to -2. Okay, so now we're going to plug that into this function. Since I'm only plugging in one number this time, I think instead of going for the whole y1 situation, I'm just going to type it in as is. It's going to be 2 divided by parentheses. It's going to be negative 1.99 squared minus 4. Just going to plug it in old school style. And I get a really big negative number, which means that we can say it's going to infinity. Negative infinity, right? There you go. Goes to. Okay, let's continue our journey here. Number 33. Now we're finding the limit of a piecewise function. Now when you're finding the limit of a piecewise function, you have to make sure the limit from the left and the right are the same. So we have to kind of do this one in pieces. We have to find the limit as x approaches 1 from the left for this function. And we're also going to find the limit as x approaches a positive 1. I'm not positive, 1 from the right is what I meant to say. Now if I'm approaching 1 from the left, that means less than 1, which means the top piece. So for the first one, I want to know what is the limit as x approaches 1 from the left of negative x plus 1. And for the right-hand side, we're doing the same thing, but with the bottom function instead, because that's the one from the right. Okay, so let's plug some stuff in. I'm not plugging in a negative one, right? I'm plugging in a positive one. That little negative means we're coming from the left. So if I plug in a negative 1, what I get is 0. Here, if I plug in a 1, I get negative 1 plus 6 minus 9. What would that be? Negative 1, 6 minus 9 is negative 3, that's negative 4. So we get negative 4 for this one. So as you see, the limit from the left is 0, but the limit from the right is 4, and that means that the limit does not exist. Okay, let's take a look at the next one. For the next one, we're only finding the limit of 2 from the right, so we're only going to use the bottom one. So the limit as x approaches 2 from the right is going to be plugging the 2 into the bottom function, which is going to give me negative 4 plus 8 minus 4, and that's 0. So this limit should come out to be 0. All right, 35. Now, if you didn't do the extra credit lesson a few weeks back on step functions, this one's going to throw you. The only way to find the limit of a step function is by doing a table. Okay, so we're going to make a table. It's a non-removable discontinuity. Step functions look like this, and those places where they are. I mean, you can try direct substitution, but the problem is that you have to understand if you end up, after you plug this in, we end up with this. And if this is an integer, then it's a non-removable discontinuity because that's where it jumps up to the next level is at integers. If you end up with a decimal, you can just get the answer. But if it's an integer, you can't. It's a non-removable discontinuity. So the only way to do it is with a table. So we're going to be approaching 3, and we're only going to come at it from the right. So what I'm going to do is I'm going to plug in a number slightly bigger than 3. All right, so how does that work? It's really easy. So if you didn't do the extra credit, you kind of missed out. It's not that bad of a thing. So we're going to plug in a number. We're going to add those. What is negative 3.001? I'm sorry, I don't want to. I'm having a bit of a brain fart. You guys are probably going to think I'm stupid, but I'm going to do this in the calculator just a second. Oops. 3.001 plus 2. There we go. So what we end up with is negative 1.001. Now here's how this thing works. What the step function does, it's also called the greatest valued function. what it does is it rounds your number down to the smallest integer closest to this number. Okay, so rounding this down would take me to the next integer below that would be -2. And so there's my answer for that. So the limit as I approach 3 from the right is going to be -2, and that would be my answer for this. -2, sorry. Now I understand that -1.001 is closer to -1 than it is to -2, but it always rounds it down. So the next integer lower than -1.001 is -2, so that's how it works. All right, so that's that one. Let's go ahead and move on to number 36. Absolute value functions. We talked about those. When it comes to an absolute value function, you have to rewrite it as a piecewise function. So first of all, we take x plus 1, and we find where it equals 0, right? And that's going to be our break-off point. For anything less than that, we're going to have to change the signs. And for anything greater than that, we don't change the signs. So to the left, I'm going to rewrite this whole thing. Oops. But I'm going to change the signs on the bottom. Or you can just put a negative in front of a pair of parentheses. But for one greater than that, we don't change the signs. Okay? Matter of fact, I think I will rewrite this as a negative in the front. And the reason for that is because we're going to simplify this. So I want to show you guys something kind of cool here. On the top, on both of these, we can factor out a 5, right? Which means this is a removable discontinuity. And so the top is -5. For all x less than or equal to -1, it's -5. But for all x greater than -1, same thing, we can factor out the 5, and the x plus 1's cancel. We have 5. And so here's the function in simplified form. So we did two things there. Probably a little overwhelming because we haven't seen this in a little while. But what you do is you take the part that's in the thing, find where it equals 0. That's your break point. To the left of that, you change the sign. To the right of it, you don't. And in this case, I removed the discontinuity also. So this problem is asking for me to find the limit of my function as x approaches -1 from the left. So that would be this one, and the answer would be -5. Now, if they asked for the limit from the right, it would be +5. If they didn't ask for left or right, but if they just said, what's the limit as x approaches -1, you would say it does not exist because it's not the same on the left and right. Okay? All right, let's move on to number 37. So, we're approaching a number, right? So we do direct substitution. That's going to give me negative, and then -1 squared is 1. -2 times -1 is 2, and then -3. On the bottom, -1 and 1 makes 0. So we already know it's undefined, and you may also notice it's 0 over 0. So you could use L'Hopital if you want to. Or you can do factoring. Remember, whenever it's polynomial, you can do factoring. I'm going to do factoring, but L'Hopital would work. So, first of all, I'm going to factor this and see if it's a removable discontinuity. I'm just going to save me some writing time. I do believe the top does factor. So these go away, and I remove the discontinuity. So now I'm left with this. We have the negative, don't forget about that. Plugging in your negative, you get -4 with a negative on the outside, which makes it +4. So the limit on that one is 4. Number 38. Just plugging it in probably is not going to work. Let's see. Maybe it will. If I plug in 0, I get a half. And half minus half is 0. And the top, oh, no, so no good. So you could do L'Hopital with this. I would highly discourage it because I think it would be very confusing. I would go ahead and stick with the strategy, though, that we learned before. When you have a complex fraction, you simplify it. So the first thing you're going to do is you're going to get rid of these little fractions on the bottom. So I'm going to start by multiplying everything by 2. And that's going to give me this. And then I'm going to multiply everything by 2 plus x. Those cancel. And now I have the following. So we have 2x times 2 plus x on the top. Just going to leave that alone. And on the bottom, we have 2 minus 1, 2 plus x. And we're going to distribute here. That's when I remember teaching this with you guys had a lot of trouble with making sure that you put parentheses on this thing when you move it around because you're forgetting to distribute your negatives and stuff like that. So be aware of that. So now we're going to have minus 2 minus x. And so the 2's cancel because 2 minus 2 is 0. You don't have to write this much, but if you can do some of this in your head. But here's what I'm left with now. And in this case, the x's can divide each other out. And the negative, I'm just going to move it to the top so it doesn't look so weird. It's going to be limit as x approaches 0 of negative 2 plus x. Direct substitution now does not give me an undefined answer. I get negative 2 times 2 plus 0, which is negative 2 times 2, which is negative 4 is my final answer. All right, let's move along. Next one, direct substitution won't work because if I plug in 4, I get square root of 4 is 2, and 2 minus 2 is 0. It's undefined. So, but this is the one with the square root. And when you have a square root, the way we talked about dealing with that is by rationalizing. You multiply the top and the bottom by the same expression, but with a plus instead of a minus. Okay, so on the top then, what we're left with is x minus 4. I'm going to put that in parentheses, and square root of x plus 2. And on the bottom, you do square root of x times square root of x, which is x, and negative 2 times 2, which is negative 4. And lo and behold, we removed the discontinuity. And we're left with this now. And we just plug it in. So now we have, plugging that in, we get the square root of 4 plus 2, which is 2 plus 2, which is 4. You're like, oh boy, all the answers are 4. I know what to bubble in on the test. I wouldn't bet on that. Let's go ahead and take a look at number 40 here. All right, now notice there's a very significant change here in the questions. I'm no longer approaching a number, but now I'm approaching infinity. So whenever that happens, you have to kind of shift your brain a little bit to a different thought. Instead of using this top table here, you're going to use this bottom table, okay? So I won't be switching back and forth with this too much, but pretty much every time you're going to be using L'Hopital. The only exception is if you have a polynomial over polynomial, and if the top is less than the bottom power, then it's 0. If they're equal, it's a over b. If it's greater, you're going to end up with either infinity or negative infinity. So let's go ahead and do this. Now in this case, you guys can see that we have a polynomial over a polynomial. The top power is less than the bottom power. That limit's going to be 0. We're done. You don't need to do anything else there. Let's take a look at number 41. In this case, it's a polynomial over a polynomial. The powers are equal. In this case, it's going to be a ratio of the coefficients. So the answer is 3. For the next one, the power on the top is greater than the power on the bottom. And when that happens, I told you guys to start by taking these two things out separately, just the front terms, reduce them, and then plug in your infinity. In that case, you have negative infinity being, oh wait, yes, negative, yeah, because I'm plugging in a positive infinity and the negative came from here. So now I've got negative infinity divided by 2, which is going to be negative infinity. So that's those ones. After that, we're going to move on to the exponential, trigonometric, and logarithmic infinity questions. And all of those are going to be solved with L'Hopital. Woo! All right. Let's take a look at number 43. So, first of all, direct substitution. The first thing I want to remind you guys of is, how did I show you guys this? I think what I told you guys was that the limit as x approaches infinity for e to the x is infinity. And I also told you that the limit as x approaches negative infinity for e to the x is 0. Okay? And I believe that's on this little sheet that I gave you guys here too. Yes, it is. Okay, so let's go ahead and do this. So we're going to plug in infinity. Now, if I plug in infinity, I get negative 3 times infinity, which is negative infinity. And here, when you do a limit with a constant, the constant just stays the same. And this is the limit of e to the x at negative infinity. So that's 0. And so the answer is 1 for this one. All right, let's go ahead and take a look at number 44. Plugging in the infinity, I get 4e to the 1 over infinity. One of the things we talked about in class is that when you have 1 over infinity, that's the equivalent of 0. And so anything to the 0 power is 1, and so 4 times 1 is 4. Whoop, well, you know, another 4 answer. All right, let's go ahead and take a look at number 45. In this case, if you plug infinity into a sine function, you get an oscillation. But on the bottom, it's going to be infinity. And then here you get 4. Now, we talked about this. And oscillation over infinity is 0. So once again, 4 again. This is stupid. I hope your test doesn't have a whole bunch of 4s on it. You guys know what to pick on the test. Just kidding. I wouldn't go by that. Okay, next one. Plugging in your infinity. It doesn't matter. The negatives don't really matter. It oscillates. And then on the top, you've got infinity. And when that happens, the limit does not exist. It oscillates. So that's number 46. Let's take a look at 47. On 47, you end up with e to the infinity over infinity squared. And then don't forget about the 2 over there, but that's just 2. It doesn't change. Now in this case, this is infinity, this is infinity. We have a L'Hopital situation on our hands here. Want to be careful not to make the mistake that I made when I did this video for you guys earlier this week, last week. You don't apply L'Hopital to the 2. The 2 is done. 2 is going to forever be there. We're just going to be applying L'Hopital to this side only. So the derivative of e to the x, I'm going to put that 2 back so we don't forget. The derivative of e to the x is e to the x. The derivative of x squared is 2x. Plugging in infinity, though, gives you infinity over infinity again. So now we need to repeat. Bring your 2 down. It doesn't go away. Derivative of e to the x is still e to the x, but the derivative of 2x is 2. Plugging infinity in, you get negative infinity over 2. All right, so now we're getting somewhere. So I've got negative infinity divided by 2. That's negative infinity, but don't forget about this plus 2 over here. Negative infinity plus 2 is just going to be negative infinity, because no matter how much you add to negative infinity, unless it's infinity, you're going to get negative infinity again. So the answer is negative infinity. All right, moving along, let's go ahead and take a look at number 48. In this case, direct substitution gives you e to the infinity minus 5. E to the infinity is infinity, and infinity minus 5 is infinity. So the final answer there would be infinity. 49. Direct sub on the top gives you infinity. I guess you could say negative infinity. Direct sub on the bottom, well, if you plug in negative infinity, this becomes 0. And cosine of 0 is 1. And so the final answer here will be negative infinity, because negative infinity divided by 1 is just going to be negative infinity. All right. Continuing on. Woo! Tired. A lot of work here. All right, so plug it in, you get negative infinity, and then plug it in here, you get cosine of 1 over infinity, which is 0, and cosine of 0 is 1, and so negative infinity times 1 is negative infinity. Chill. All right, last two problems here. Direct sub gives me 0 over ln of 1 is 0, so that's a L'Hopital problem. All right, so the derivative of the top is 1. The derivative of the bottom is 1 over x. Simplifying this expression by multiplying the little denominator gives me x. So now this expression can be rewritten as the limit of x as x approaches 1, and the answer is 1. Let's take a look at the next one here. ln of infinity squared is ln of infinity, which is infinity. Infinity here is ln of infinity plus 2 cubed. Well, infinity plus 2 is infinity, and infinity cubed is infinity, so I've got infinity again. So it's infinity over infinity, so we're going to do L'Hopital. So the derivative of the top is going to be 1 over x squared times the derivative of x squared, which is 2x, which simplifies to 2 over x. Derivative of the bottom is going to be 1 over x plus 2 cubed times the derivative of the inside, which is going to be multiply the front, take 1 off the power, and then this crosses off 3 of those in the bottom, and so we're left with 3 over x plus 2. All right, so now we're going to find the limit as x approaches infinity of these derivatives here. So I've got 2 over x over 3 over x plus 2. All right, so we need to simplify this fraction. Now, one way is you can multiply the top and bottom by x. Which gives us 2, not 2x, 2 over 3x over x plus 2. Then you multiply the top and bottom by x plus 2. And so now we have the limit as x approaches infinity of 2 times x plus 2 over 3x. Okay. We can distribute here. That's going to give me 2x plus 2 over 3x. Now, this looks familiar. You could just plug in again. You're going to get infinity over infinity, right? And then just do L'Hopital one more time. And you end up with the limit of this of 2/3, which is just 2/3. But in case you didn't notice, even though that's our final answer, but in case you guys didn't notice, we could have used that shortcut where the power on the top, power on the bottom is the same, so it's just going to be those two numbers. But you can also just apply L'Hopital again and take the derivative of the top, which is 2, derivative of the bottom, which is 3. The limit of a constant is just the constant, and get 2/3. So 2 ways to handle that one, but anyway, there you go. So that's your whole study guide. Oh, no, it isn't. We've got a few more questions here. Hooray! The following types will be extra credit. I won't go over those, but let's move on to number 53. I didn't realize we stopped at 50. Let's keep going. Prove that the piecewise function is continuous at x equals 1. You'll see one of these on your free response question, just so you guys know. So to prove that this function is continuous, we need to show that f of -1 is equal to the limit of f of x as x approaches -1. So first of all, let's find out what f of -1 is. f of -1, you're going to find where it equals -1, and you're going to use that piece, and you're going to plug -1 into that piece. And so that gives me -2 minus 2, which is -3. Then we got to find the limit. Now, we talked about how you find the limit of a piecewise function. You find the limit from the left and you find the limit from the right. Now, if I'm finding it from the left, that means less than, which means I'm using 2x minus 1. So I'm going to do 2x minus 1, and I'm plugging in -1. And then the limit from the right, that means I'm using the bottom one. So I'm plugging in -1 into the bottom function, which is x squared minus 4. So in this case, I get -2 minus 1, which is -3. And here I get 1 minus 4, which is also -3. So there it is. And therefore, we've proven this. So you have to find the value of the function. You have to prove that the limits from the left and right are the same, and that those two values you got are actually equivalent to the function's value, which is what we stated in the beginning there. So to get how this is going to be graded on your guys' FRQ is you're going to get 1 point for finding the value of your function. You're going to get 1 point for finding the limits from the left and from the right. And then you're going to get 1 point for making your final statement that those two things are equivalent. Okay? All right, moving along. Let's go ahead and take a look at number 54. In each situation below, we cannot apply the intermediate value theorem. Explain why. So basically, there are 3 criteria that are required in order to use the IVT. First of all, the function has to be continuous on the interval. Also, f of a cannot be equal to f of b. If they are equal, it doesn't apply. And then third of all, the k value you're trying to work with has to be in between the two values, y values that you're concerned with. So for number 1, let's see which one of these fail. Let's make sure it's continuous on the interval. This is a rational function. Rational functions have discontinuities where the denominator equals 0. So the denominator equals 0 when x equals 4. And is 4 on the interval? The answer is yes. So therefore, there is a discontinuity on the interval. So that's why we cannot apply the IVT on this problem. It's not continuous on the interval. There is a discontinuity present. Let's take a look at part B. Given that y equals 3x minus 2, why can't we use the IVT to prove that there must be some value of c? Well, this is a linear function, so it's always continuous. So it doesn't matter what the interval is, it's always continuous. So that's not the problem. Let's see. If we want to make sure that f of a is not equal to f of b. So let's plug in our a and b. So this is going to be -2, and this is going to be 13. They're not equal, so that's good. So that means the only reason why this can't work is because our k value must not be in between there, and that is indeed the fact. Here's my k value. Is 20 in between those two numbers? And the answer is no. So here's our reason then for part B. Because k is not between f of, or I guess we could be more specific. Instead of saying k, we could just say 20. Because 20 is not between f of 0 and f of 5. Or you could just use the numbers that we got, which was what? Like -2 and 13. All right, now that is the end of our study guide. The rest of those are extra credit. I'm not going to go over those. Those are just for you guys to practice with. I will tell you the answers, though. But if you want those, then you should have done the extra credit. So that's still available, by the way, but I'm sure you guys are busy. But there you go. And there you guys go.